Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture, we will continue our discussion on machine learned interatomic potentials. Just as a recap of what we did in the last couple of lectures. So, we started out with the introduction on classical machine learned interatomic potentials. These are atom centered models where you fingerprint a given local environment or coordination environment using different descriptors. And these can either be models that are linear or non-linear in energy and also other quantities such as forces and stresses. So, we took a specific example of moment tensor potentials and we looked at how it is mathematically implemented. And some of the drawbacks of classical machine learning interatomic potentials are their low learning rates and also lack of transferability across different systems. Some of these drawbacks can be sort of improved upon or mitigated by incorporating equivariance and message passing. So, we looked at what equivariance is. So, there are vectorial and tensorial properties of materials that change according to rotation or reflection of your input structure. So, if your network, if your neural network model or machine learned model understands those mathematical operations of rotation and reflection and it is invariant to translation, then it is typically referred to as an equivariant model. And in we also looked at how message passing is advantageous in graph neural networks in the sense that you can capture longer ranged interactions quite efficiently compared to classical machine learning interatomic potentials. So, we looked at the example of graph neural networks and the specific example of neural equivariant interatomic potentials or NEQUIP, which uses or which splits the messages into a radial basis and spherical harmonics basis. So, radial basis for sort of indicating the extent to which bonds contribute, spherical harmonics to the extent to which many body interactions and sort of orientations contribute. And in general these sort of graph neural networks encode two body information. So, in the form of bonds basically. So, that is where we sort of stopped in the last lecture. So, today we will look at ways to create sort of more generalizable machine learning interatomic potentials. So, are there frameworks which can sort of learn over a wide range of material systems, elements and so on, and basically achieve quite high accuracies across a wide diversity of systems. So, those types of models are what are referred to as generalizable machine learning interatomic potentials. So, we will see whether there are mathematical or systematic ways to create more generalizable and more accurate machine learning interatomic potentials. Alright. So, in order to understand generalization, right, so we have to go back in time a little bit and understand what is referred to as atomic cluster expansion or ACE. So, the questions that we will try to answer are that are classical MLIPs and message passing. So, those that are based on graph networks MLIPs, are they actually fundamentally different by construction or are they not? So, can they be derived as special cases or special scenarios of an overall mathematical framework. So, that is one of the first questions that we will try to answer in this lecture. The second one is, are there more systematic ways to generate better MLIPs. So, in other words, can you keep improving the accuracies of MLIPs across a wide variety of systems. Because if there are more systematic ways, then we can always find ways to get better accuracy. If it is just hyperparameter optimization or feature engineering, then it is not necessarily a systematic way to generate better MLIPs, because one set of hyperparameters may always work for one subset of systems and may not generalize well for other systems. And the final question that we will try to answer is, can MLIPs be foundational? So, in other words, can you have one MLIP that works for the entire periodic table, right. So, we would like to see such MLIPs being constructed simply because it can increase the speed at which we can discover new materials. So, we will try to see if there is a way to construct one MLIP for the entire periodic table and also combination of elements within the periodic table. So, not just for elemental systems, but also for combinations of elements. So, this could in fact replace or at least reduce the number of classical computations that we would need right, to discover or identify new material candidates. in order to answer all these three questions, so are classical and modern machine learning interatommic potentials fundamentally different? Are there systematic ways to generate better MLIPs, and can MLIPs be foundational? So in order to answer these questions, we need to revisit this atomic cluster expansion mathematical formalism. So what is the atomic cluster expansion? So so you can, if you think of a structure, so any given structure is basically a collection of atoms, and a structure can have an energy associated with these collection of atoms, right. So you can actually write the energy of any given structure which is made up of these collection of atoms arbitrarily in the form of this type of an expansion, right. So this is a constant term, this is basically terms associated with individual atoms, these are sort of interactions associated with individual bonds, these are triplet interactions, these are quadruplet interactions, and so on. This is an arbitrary expansion, so basically we are saying that energy of any given system has a constant term, so think of this as a bias term, right, and then you have you know, energy is dependent on how many of a given type of atom you have, right, in your structure. So if it is sodium chloride, so there will be one sort of interaction term for sodium and one interaction term for chlorine. And then pairs of atoms can interact, so that can also contribute. The 1/2 is basically to ensure that, you know, we are not double counting pairs. Same case with triplets, right. So 3 atoms can have a common set of interactions, same case with quadruplets, 4 atoms can have a common set of interactions, and so on, right. So you can keep generalizing this expansion and you know, have quintuplet, you know, 6 term interactions, and so on. So this is the energy of a given structure. Now you can sort of decompose the energy of a given structure in terms of its individual you know, atoms, right. So I basically stands for an atom within the structure, so you can write the energy as a summation of EIs, just like how we have done it for our you know, machine learning interatommic potential so far. And the individual EI term, so the energy of an atom within the structure can be written as, excluding this constant term, we can sort of write it as the energy associated with that atom at that site, right, and then all the pair interactions that the central atom will have with respect to its nearest neighbors or next nearest neighbors, and so on, all the triplet interactions, all the quadruplet interactions, and so on, right. So you can sort of think of this as a projection of your individual atomic energies onto the overall energy, right. So you take a projection, so you sort of isolate all the Ri terms basically, so V1 of Ri, V2 of Ri, V3 of Ri, and so on, right. So this is a fairly straightforward extension of you know, decomposing your total energy into individual atomic energies, and this expansion is fairly general. So this can be you know, the range of interactions of atoms when you expand it in this form, so pairs, triplets, quadruplets, and so on, forms a complete basis, and hence you can arbitrarily write the energy of an atomic energy of an atom in a structure in this form with you know, varying degrees of accuracy. So the more terms you include, the more accurate your atomic energy is, right. So this can be written in a mathematically rigorous form. The only or the major difficulty with writing your atomic energy in this form is that it is very, very difficult to compute. Right. So if you have k terms, so k refers to the complexity of interactions that you are considering. So this would be k equals 1, this could be k equals 2, this could be k equals 3, and so on. So this is k equals 2 basically indicates that it is a pair interaction, k equals 3 is triplet interaction, and so on, right. So if you were to consider sort of roughly k terms here, right, k plus 1 terms, the computational time associated with that is basically n power k, where n is the average number of neighbors that you have for a given central atom I, right. So the more number of neighbors and the more complexity of your terms, you see that the computational cost can blow up very, very easily, right. So if you take a simple BCC structure, right, so your n could be 8 here for instance, and if you were to consider let us say triplet interactions, right, so this could be 8 power 3, so that is already, you know, quite a huge number in terms of your computational cost, and if you gradually keep increasing the number of atoms, keep increasing the range of interactions, this number is going to blow up very quickly, right. So this expansion is extremely difficult to compute, and hence we need some kind of mathematical tricks to make these computations tractable, right. And what type of tricks do we introduce? So we want to expand atomic energy as a form of some kind of interactions, right. So, as the form of pair interactions, triplet interactions and so on. So, in the form of some interactions, but maybe if we map these interactions onto a better set of basis functions, maybe we can reduce the computational cost and ensure that it is not n power k and it's maybe scales as n or 2 power k or something like that, right. So, we can try to reduce the computational cost by changing the extent of or by changing the kind of basis functions that we are using to expand these terms. Now, the key idea behind this atomic cluster expansion is the fact that energy of a given atom, right, actually depends on the kinds of bonds it forms, right. So, the energy of an atom depends on its bonds. So, the bonds are in your pair terms, in your triplet terms and so on. And each bond per se depends on the relative positions of atoms more than the absolute positions, right. So, even if you translate a unit cell within a structure, the energy of that unit cell should be the same, right. So, it does not matter whether you put your origin of your BCC cell in the corner of the cube or in the body centered position of the cube, right. The energy of that cube should be the same. So, the energy depends on bonds and each bond basically depends on relative positions instead of absolute positions. So, if you look at all of these expansions, right. So, Ra basically stands for the position vector of the ith atom within the structure. So, this is an absolute position. So, maybe we can try to modify this into some kind of a relative position, so that the complexity of these terms, I mean that could be one way to reduce the complexity of these terms, right. So, the energies depend on bonds, bonds depend on relative positions of atoms. So, we will introduce what is referred to as a particle basis. So, we will look at what is particle basis in the next slide, and this you will see that it is orthogonal and complete by construction. So, it is a valid form of expanding your energy. And once you introduce this kind of a basis, you can then group a bunch of bonds and form essentially what are clusters, right. And then once you group bonds in the form of clusters, you can basically expand on those different clusters, basically have a cluster expansion to get an energy associated with an atom, right. So, that is why the name of this mathematical formalism is atomic cluster expansion or ACE. It has analogies to the cluster expansion lattice model that we saw before, and we will see what those analogies are in the next few slides. Okay. So, just to reiterate the idea, so the energies depend on bonds. So, if you want to introduce a new particle basis, and once we introduce this particle basis, maybe we can group these bonds into clusters and then expand on these clusters, right. So, how do we do that mathematically? So, let us say you have you consider a cluster, right, a cluster of atoms containing k bonds, right. So, the bonds could be you know two bonds which is a pair cluster, 3 bonds could be triplet cluster, 4 bonds could be quadruplet cluster and so on. So, alpha is a cluster consisting of k bonds. So, you can now sort of write a particle basis. So, alpha is your cluster and nu is basically the number of bonds within your cluster itself, right. So, you can now write this as a product of some kind of a function, right, of your pair interactions here. So, this basically says Rj1 of I. So, I is your atom of interest, J1 is one of your neighbors, and this is J2 of I, right, and so on up to Jk of I, right. So, you can now expand your pair interactions basically as the product of all the pair type of bonds that your central atom forms within your given structure, right. So, once you and each phi here, each phi term here basically depends on bond lengths themselves. So, these depend on relative positions and not absolute positions, right. And each phi here you can sort of expand in turn with some kind of radial basis and spherical harmonics. So, you can sort of make sure that each phi encodes relative you know positions or bond lengths, and the spherical harmonics basically ensures that you take into account some kind of angular interactions as well. Right. So, you sort of decompose all the you know a cluster of atoms containing k bonds into a product of all the different types of bonds that you can actually form, right, within that cluster. And once you define a cluster, you can now define several types of clusters here. So you can keep generalizing your alpha. So alpha can again be pairs. So I am indicating all the pair interactions here. Alpha can be triplets, quadruplets, and so on, right. So the type of interactions that you encode in a cluster, it depends on the complexity of the system. So you can keep increasing the complexity. So once you define a set of capital phi values here or functions here, you can now write your overall atomic energy. So this is individual atomic energy as a function of the arrangement of atoms, the configuration of atoms, and this can be written as a constant term plus some kind of a j times phi term here. So each phi, the value of phi here depends on the configuration itself. J is basically how the strength of interactions of atoms within each cluster, right, and you sort of sum it over all the clusters and individual bonds within a cluster, right. So if you do that, you basically get your atomic energy, and if you do this for all the atoms, you basically get your total energy of your system, right. So if you look at this energy, right, this energy expansion term here, this has a lot of similarities to the cluster expansion formalism that we saw a few lectures back, right. The key difference is that in your cluster expansion, your left hand side of the equation is basically your total energy of the system, right, and your J's are basically effective cluster interactions or screened interaction terms in your regular cluster expansion. So you are still trying to predict your total energy of your configuration in your regular cluster expansion. Here you are trying to predict individual atomic energies as a function of their configurations, as a function of different distributions of atoms in your structure. So this is still an interatomic potential. So you are trying to predict the energy of an individual atom here, right, and once you know the energy of all the atoms in your system, you can still take the derivative of the energies and get forces, right. So this is a way to still get an interatomic potential, whereas a cluster expansion is still an energy model, it is still a lattice model. So those are the differences, but you also see the similarities between your regular cluster expansion and the atomic cluster expansion here, right. So just as notation here, right, so sigma is basically configuration of atoms, nu is a collection of bonds within a cluster alpha, and this expansion looks similar to a cluster expansion, right. But note that we have not solved the computational problem yet. So we have not solved the scaling problem, the n power k scaling problem yet. We have simply transferred all the unknowns into this phi term here, or this phi term here, right. So we still need to figure out how to expand this phi basis, right, and these phi terms are basically referred to as the particle basis here, right. So we still need to figure out how to expand this particle basis so that we solve the computational scaling problem. Okay. So the way to solve this computational scaling problem is we take this particle basis and then we modify it slightly and create what is referred to as the product basis, right. So before we do that, let us see how we can expand our individual particle functions. So you have a phi function here. So this phi, small phi, is the same as this small phi here, right. So we have these individual particle functions here, phi's, right. K and nu are basically indices to keep track of the individual functions, right. K basically stands for some uncoupled indices, right. So these refer to elemental identity, positions, and so on. CL and M basically correspond to coupled indices. Basically these capture bonds, ensures equivariance, and so on, and these indices are all element agnostic. So they do not care about what individual elements you consider for constructing this phi, right. So you can now write this individual particle functions phi of kV as an expansion of your radial basis functions, right, your spherical harmonics, right, YLM here, and TKC, your T basically stands for the elemental identity, right. So these are basically features that identify your element I, so that is theta I here, and your element J, that is theta J here, right. So radial basis functions take relative positions of atoms, spherical harmonics take in the actual position vectors, and then they take the angular component out of them. So they expand them in terms of angles, right. So so the spherical harmonics are basically there to ensure equivariance. Using radial basis functions basically ensures translational invariance, and then you have this these T functions basically to ensure that you retain the elemental information, right, so that each phi has knowledge of what elements constitute a given cluster, given particle function. So once you expand your particle functions like this, right, you can now introduce a new basis which we refer to as the atomic basis, right. So basically this think of this atomic basis as a kind of projection of your density around each atom, right. So how many bonds does a given atom form within some kind of a spherical cutoff, right. So the way we define this atomic function is fairly straightforward. So we write this as A of I, so I is your atom of interest here, right, and K and U are the same indices that we are using here, right. So A of I is basically summation over all the neighbors, right, all the neighbors of your atom I, and we basically write your atomic basis as just a simple summation of your phi of phi of K nu, right. So phi of K nu, each phi basically corresponds to one bond, right, and you basically sum over all the bonds within some kind of a cutoff distance, a spherical cutoff distance for example, and that basically gives you your atomic basis. So if each phi is a bond and you are basically summing over all the bonds, basically you are counting all the bonds within a cutoff, right, and that is the definition of your atomic basis, right. Now once you have your atomic basis, so you kind of know how many bonds are there around each atom, you can, without losing any generality, you can now define something called a product basis, whereby you can capture higher body interactions, right, by taking products of A around different around the same atom, right, but multiple times. So basically what I mean is, so I introduce what is referred to as a product basis, right. So I take the product basis as the product as the sort of term by term product of my individual atomic basis over multiple times, right. So this basically ensures that for a given atom, so if I introduce an atomic basis, I basically count all the bonds within a cutoff distance for a given atom. So if you imagine a sphere around an atom, I basically know how many bonds that your central atom is actually forming, right. Now I am going to take that atomic basis and then take products of itself multiple times. And if I take products of itself multiple times, basically I can capture higher body interactions, because not only I am going to multiply the same bond with itself, I am going to multiply one given bond with all the other bonds, right, within your cutoff distance, right. When you do that multiple times, you can basically encode some kind of higher body interactions, right. So 2 body, 3 body, 4 body interactions around a given central atom, right. So we can, using this product basis, we can have a systematic way by which we can encode higher body interactions in a fairly straightforward fashion. Now that what I explained in the last slide can be a little non-intuitive to imagine, so let's this graphic should help ease in the visualization, right. So just as a recap, we have introduced this product basis, which is basically taking the number of bonds around a given central atom and then multiplying each bond with itself multiple times, right, with itself and all the other bonds multiple times, right, and how many times we multiplied is basically indicated by this nu factor here, right. So how to visualize this graphically? So let us say you have a central atom of interest, right, and this is your spherical cutoff here. You have now counted all the bonds within your central atom, right. So the energy of this atom of interest is going to be influenced by all of these bonds, right, and all of these bonds are going to influence it by the way of pair interactions. So those are individual bonds going to contribute to the atomic energy here, triplet interactions, quadruplet interactions and so on, right. So if you write your atomic energy, the individual atomic energy, as an expansion of, let us say, pair interactions here, triplet interactions here, quadruplet interactions, quintuplet interactions and so on, this is the classic definition of your atomic cluster expansion, right, and this scales very badly. This has the n power k scaling problem. But using your product basis, what you can basically do is, so you can write your energy of your atom here, right, as the energy of that product basis term itself, right, and we then take the product of the basis with itself, right. So here we are going to multiply, let us say, this bond with not only itself, right, but with also with all the other bonds, right. So when we multiply one product basis with itself once, we are already capturing 3 body interactions, right, and when we multiply it let us say 2 times, right, we are capturing 4 body interactions and so on, right. So if we multiply it more number of times, the product basis with itself, just because we are multiplying one bond with other bonds, right, within the cutoff distance, just by that fact we are able to capture many body interactions, right. Now the good thing is, in this case, right, in the former case, you have to identify all the pairs first, right, and then write an expansion in terms of pairs, identify all the triplets, and then write an expansion of all the triplets, identify all the quadruplets, and write an expansion of all the quadruplets, and so on. So this identification and then writing it as the summation of individual pairs, triplets, and quadruplets is what leads to this poor scaling, this n power k scaling here. But in this case, all you need to do is calculate the number of bonds or count the number of bonds once, right, and you simply store all the bonds, right, within your cutoff distance, and you keep multiplying the same number of bonds with itself. So it's an element by element multiplication, which is a simple matrix multiplication. So this multiplication cost is quite trivial. So if you want to multiply this matrix with itself, it's quite a trivial cost. You can multiply the same matrix 2 times, that is also a trivial cost, and so on. So your computational cost doesn't really scale dramatically as you keep multiplying the matrix terms with itself, right. And at the same time you are capturing higher body interactions. So you take this, you basically capture all the pair interactions, you do this, you take a product once, you capture all the triplet interactions, do the product twice, you capture all the quadruplet interactions, and so on. So expanding your energy in this form, in the form of your product basis, so recollect that each individual term is a product basis. So this is a product basis multiplied with itself, product basis multiplied with itself twice, and so on, right. So if you write your energy as an expansion of your product basis, right, you now get linear scaling behavior, right. So we have now solved the mathematically intractable problem of n power k scaling with a simple linear scaling model, right, whereby we have used this definition of product basis to count the number of bonds, and then we encode many body interactions by multiplying that same product basis with itself multiple times, right. But we are not done yet, so we are almost there. We have solved the computational complexity problem. The next thing to do is to somehow integrate this product basis with message passing, right, so that we can use graph neural networks and introduce the principles of equivariance and so on, right. And that's where this principle of symmetrized basis comes in, right. So introducing the symmetrized basis basically ensures that you are including equivariance in your model. So the crux of what we do is, so let's say you have the product of you have the product basis here, you want to make this product basis equivariant, right, which implies the definition of this product basis, right, should be equivariant to any transformation that you are using, that you are doing, right. So the representation of your transformed basis should be the same as the transformation of your representation of your basis, right. So that's the principle or crux of equivariance. So if you build an equivariance with this into this product basis, basically the resultant basis functions that you get is what is referred to as symmetrized basis, right. So the way we sort of define symmetrized basis is using this B term here, right. So we introduce equivariance through this integral term, right. I mean, this is the rigorous way to define equivariant or build an equivariance to this product basis and get a resultant symmetrized basis. This is a rigorous way to do it, but in practice what we do is we basically take our B terms, so these are symmetrized basis, so they are equivariant by construction. We take this as a simple summation of the product basis multiplied by the so called Clebsch-Gordan coefficients, right. So these coefficients basically indicate or basically build in equivariance into our basis function itself, into our symmetrized basis function. So the way sort of Clebsch-Gordan coefficients work is whenever you have a rotation, reflection, and so on, they sort of identify how the representation is actually rotated or how the representation is actually reflected. So these consist of specific terms from group theory representation. So think of these as specific matrix terms, and when they multiply themselves with your product basis, only a select few terms survive, right. And those survived terms are basically represent the rotated or transformed version of your original representation. So doing this process, so I know this is mathematically a little complex, but if you do this process of expanding your symmetrized basis as a summation of Clebsch-Gordan coefficient matrices times your product basis, the resultant symmetrized basis is equivariant by construction, right. So we have built in equivariance in a fairly systematic fashion, right. So now that we have defined our symmetrized basis, we can now go ahead and write our energy of your atom in a given configuration as just a linear summation of your weight terms times your BI terms, your symmetrized basis terms, right. These weight terms can be your learnable weights, and if you expand your atomic energies in this form, right. So summation of your weight terms times your equivariant symmetrized basis, this type of an mathematical framework is what is referred to as linear atomic cluster expansion or linear ACE, right. And this linear summation, if you look at it, I mean it is it looks like a fairly simple model, right. So your omegas are the learnable weights, and B basically is fingerprinting your local atomic environment, right. And we have fingerprinted by way of first defining our particle basis, then we went to atomic basis, then we went to product basis, and we finally got symmetrized basis, right. Now if you change how you got these B's through defining moment tensors and then defining contractions of moment tensors and then expanding moment tensors up to a certain level, you basically get your moment tensor potential, right. So moment tensor potentials differ from linear atomic cluster expansion only in the way that they generate your BI terms here, right, and whether or not they build in equivariance here. So moment tensor potentials as they have been developed do not build in equivariance, right, but if they build in equivariance, then the basis functions are different, then you can sort of write that as a different potential term, you can write that as a linear ACE potential term, right. So the sort of nice thing to know about this type of a mathematical form, right, where you write your atomic energy as a function of learnable weights times some kind of a fingerprint of your local atomic environment, is that any classical machine learned interatomic potential, right, can be derived as a special case of the atomic cluster expansion or the linear atomic cluster expansion, right. And all classical MLIPs basically differ in the way that they choose their basis sets for defining this fingerprints, right, whether they build in equivariance or not, and how many body order interactions. So whether it's only pairs, they count only bonds, whether it's triplets, quadruplets and so on. So how many body order interactions are they actually including in the definition of their atomic energy, right. So we can see that the atomic cluster expansion provides a very simple, elegant mathematical framework that overarches or extends over all classical MLIPs, right. So in other words, all classical MLIPs can be defined as special cases of your atomic cluster expansion, right. So just as a summary, right, so initially we started off with some kind of atoms, right, then we introduced particle basis which took in relative distances into account, then we extended towards atomic basis where we counted the number of bonds, right. Then we defined the product basis where we started taking in higher body order interactions. So not just bonds, we also took into account pair interactions, we also took into account triplet interactions, quadruplet interactions and so on. And then the final transformation of symmetrized basis where we bake in equivariance, we build in equivariance to our product basis here, right. So if we do all this in a systematic fashion, the resultant is your linear atomic cluster expansion. So the final thing that we probably need to do, so we see that atomic cluster expansion is a fairly general mathematical framework, and up to this point we can basically define or generalize all classical machine learning interatomic potentials as special cases of your atomic cluster expansion, right. But we also saw the importance of message passing in our previous lecture, and message passing as being a powerful technique that can be combined with graph neural networks. So how do we ensure we can incorporate message passing into this atomic cluster expansion framework, right. So we do that just like how we do message passing in the simpler interatomic potentials that we saw before in the simpler graph based interatomic potentials that we saw before, whereby we add in the message passing, or we ensure that the messages that are being passed across the different nodes, right, different nodes in your system are equivariant by construction, and they have weights associated with them, right. So individual messages, right, are now expanded as a summation of the associated weight terms and the individual symmetrized basis terms, right. So we see that according to our definition of BIs, these BI terms should already be equivariant. So we have already baked in equivariance here, and these W terms are your learnable weights, right. So each time your message gets updated, your weights will get updated, right. And once you have your messages, right, once you accumulate messages for all the nodes that are linking to your central node, central atom here, you can then update the features, update the learnable features of your central atom, right. And once you update the learnable features of your central atom, you can then pass them, you can do this message passing multiple times, you can get a final set of embeddings like final pooling layer, and beyond which you can use either simple MLPs or some kind of readout functions as defined here to generate your atomic energies, right. So that is how you incorporate your message passing along with your atomic cluster expansion framework, right. And if you do this, so if you incorporate message passing along with the atomic cluster expansion framework, the resultant mathematical interatomic potential framework that you get is what is referred to as MACE, right. MACE is basically ACE, the atomic cluster expansion framework with message passing, right. So just to go through all the equations here, right. So we basically define our messages as functions of our symmetrized basis here and learnable weights, right. And once we accumulate messages, we then pass them through some kind of an update function here, which updates the learnable features of a given node, right. So these are the existing features, these are the messages that you get, right. So you put together both of them, and the choice of how you add them or take the average or take the maximum, I mean those are all design choices, right. And then once you do this message passing multiple times, you can then finally define your atomic energy, and in the MACE framework we typically use a readout function, right, and the readout function is basically a MLP, a multi-layer perceptron, a dense neural network. So we pass in all the we pass in a flattened set of learnable features into this MLP, which then gives out a set of weights and biases, right, and those weights and biases contribute to this readout function, right. Think of this as some kind of an activation function which gives you your individual atomic energies, right, and these individual atomic energies can then be added up to get your overall overall structural energy, right. And we see that the individual atomic energies can keep getting updated the more times you do message passing here, right. So that's the basic idea behind your MACE architecture here. Multi-ACE or message passing ACE or MACE basically does message passing on your ACE symmetrized basis. So you combine your ACE symmetrized basis, you define your messages in the form of asymmetrized basis, and then once you incorporate message passing, the resultant is what you get as MACE, right. So MACE itself combines message passing on your symmetrized basis, it has linear update functions here, so it's just a linear summation of both, and then it has non-linear readout functions here to get your individual atomic energies as at any given iteration of message passing. So T stands for how many message passes you have incorporated in your framework. So now we can actually see that any message passing MLIP, so any machine learning interatomic potential that is based on graph networks can be considered as a special case of MACE, right. So MACE provides the mathematical framework or the most general framework, and all of your graph based interatomic potentials can be considered as special cases of your MACE potential here, right. So how do the individual interatomic potentials differ? They differ in the choice of basis, so how you actually expand your BI terms here. They differ in the choice of update functions, whether they are linear, pool, they introduce some kind of pooling functions here. What body order do they consider? Do they only count bonds? Do they count triplets, count quadruplets and so on, and whether they build in equivariance or not in your messages, So depending on these 4 choices, you can consider any message passing machine learning interatomic potential, any graph based network as a subset of your overall maze architecture. So this slide sort of summarizes what we discussed in the previous slide, that maze provides an overarching mathematical framework where all the individual graph based machine learning interatomic potentials that have been developed so far can all be considered as subsets or special cases of your maze, right. So if you take the example of SNET and NeckWhip, so NeckWhip we discussed in the previous lecture. SNET is another graph based neural network potential, and these two can be considered as special cases of maze based on how they define their message functions. So what kind of basis set they use, what kind of update or pooling operations they use, what kind of pooling operations they use and what kind of update functions they use, right. And there are also other graph based potentials that are listed here, and how they differ in their construction compared to your classic maze is also listed here, right. So the sort of new here basically, or what is referred to as local correlation order in this term basically refers to as body order, right. So if nu equals 1, basically the individual potentials count all the pairs, so or consider all the pair interactions. If nu equals 2, they consider triplet interactions and so on. The total correlation order is basically the total amount of interactions that you actually capture in your potential, and this you can write as nu times t. So t is the total number of message passing layers that you have, right, and nu is the total body order you have, right. So if you have triplet interactions, right, so that would be 2 and then 3 message passing terms, you basically have a total correlation order of about 6, right. So you can capture fairly long range and fairly complex interactions by increasing your body order and by increasing your message passing. So message passing increases your range and body order increases the complexity of your interactions, right. So total correlation order basically tells you what is the total complexity and range of interactions that your model is actually capturing, right. So you can now consider all the different graph based models as subsets of your maze framework. Okay, so just to give an idea of the importance of body order, so or the complexity of interactions, these 3 plots show how models evolve, right. So these are all subsets of the maze architecture itself, and they all vary based on what kind of equivariance they introduce and what kind of body order they consider, right. So we are basically tracking the mean absolute error in atomic forces here as a function of number of training data, right, and the data set here is a molecular data set, right. This is a fairly standard well known data set. So what do we see here, right. So if you look at the first plot, what it basically says is that higher body order, right, changes the order or the slope of the learning rate, right. So the steeper the slope is, right, the faster the errors actually decrease with increasing the number of training data, and the faster your models actually learn, right. So if you look at the triangles here correspond to lower body order. So nu equals 1 basically indicates that this only captures pair interactions. This is triplet interactions and this is quadruplet interactions. So we see that once you start introducing quadruplet interactions within your model converges much faster, it learns much better compared to if you just considered pair interactions, right. So higher body order seems to be important, right. And this plot here basically indicates that equivariance, right. So if you include equivariance, it basically leads to a shift, right, in how the models actually learn, but it does not change the slope, it does not really change the slope here, right. So what do I mean by that? So if you consider these 3 plots here, all of them correspond to the same body order, so all of them consider quadruplet interactions, but the amount of equivariance that is being considered is different. So 0 basically means that there is no equivariance, so you only consider scalar terms. L equals 1 basically indicates that all the vectors are equivariant in your model. L equals to 2 considers that all the second order tensors are equivariant in your model, right. So if you now introduce second order tensor equivariance, right, the models do learn faster, right, but it is a linear shift, right, in your learning rate. So the models start off at a better error range, right, when you have more equivariance compared to when you have less equivariance, but the models learn at the same rate, right. So the slopes are the same, right. So that's what the second plot indicates, and the third plot indicates that equivariance can introduce a change in slope only when you have a small body orders. Right. So if you for example all of these three plots here, all of these three symbols consider only pair interactions, so nu equals 1 here, fairly simple interactions, and when you consider only simple interactions, then when you build in more equivariance, right. So these are no equivariance, this is vector, this is tensor, second order tensor equivariance. So when you consider very simple interactions, only pair interactions, their equivariance seems to change the slope slightly, so it seems to affect the learning rate. If you are already considering fairly high body order terms, so a fairly high complexity of interactions, then equivariance only leads to a linear shift in your learning rate, it does not really change the slope. But the most significant impact in terms of your learning rate comes from your body order itself. So the more complexity of interactions you actually account for, the faster your models actually learn. Right. So there is also a trade off here. So the faster the more complexity of interactions that you actually introduce into your model, the faster your models learn in terms of number of training data, but the models may require more computational resources, right. So they may require more memory, they may take more number of more computational time or resources per epoch of training and so on. So the training cost and in some cases even the deployment cost may go up as you keep increasing your body order, right, but that leads to higher learning rates and typically that also leads to higher accuracy. And the other interesting thing to learn about maze is that it seems to learn quicker with fewer layers, with fewer message passing layers compared to other standard networks that that we actually have available. So NeckWhip and Botnet are other special cases of maze, right. So these are, both of these are graph based networks, and we see that in all the cases maze sort of decays in its root mean squared errors. So these are root mean squared errors and forces in energies at different temperatures. We see that in all the cases maze sort of decays its root mean square errors much faster. So even with two number of message passing layers, right, with two message passing layers, maze achieves fairly good accuracy, right, and accuracy improvement is not significant as you increase more number of layers, right. So maze converges to fairly accurate models much more quickly with fewer message passing layers compared to other graph based networks that are there, right. So we have now considered two things, right. So one is we have found a way to mathematically or provide a mathematical framework where we can consider all the classical and graph based neural network potentials in one framework. So all classical potentials are subsets of the atomic cluster expansion, all the neural network potentials, all the graph based neural network potentials are all subsets of your message passing ACE, right, or maze framework. So we have now considered we have built up a mathematical framework and we see the importance of both body order and equivariance, right. So given that maze provides a theoretical basis, right, for combining message passing, equivariance and higher body order interactions within machine learning interatomic potentials, now we can go ahead and try to answer the third question, right. So can foundational models be now constructed with maze, right. So maze provides a fairly theoretical framework, it also provides a fairly systematic framework for improving the accuracy. So the higher the body order terms that you incorporate, the more equivariance that you actually build into your model, the more accurate your model is going to be, right. So the systematic ways by which you can make your model accurate, it also provides a general mathematical framework for combining both classical machine learning interatomic potentials and graph based machine learning interatomic potentials. So we answered 2 out of the 3 questions that we started off in today's lecture. So the final question is, can foundational models be now constructed with this maze framework? The answer is yes. So you can indeed use maze to construct a foundation model that works for more or less the entire periodic table and all the combinations of elements within the periodic table, and that model is referred to as maze MP0. Right, MP stands for materials project. So materials project is the data set that they use to train this maze model. 0 is the version number here, right. So they trained on what is referred to as materials project trajectory data set. So trajectory data set basically contains about 1.5 million structures. So if you take the case of any structure and do a simple DFT calculation, you would see that the structure actually relaxes, in the sense that structure actually changes as it tries to arrive at its ground state. So in the materials project trajectory data set, the trajectory or the structures that a given initial structure samples on its way to the ground state are actually saved, right. So you have the individual structures and their corresponding energies and atomic forces. So this is a fairly useful data set to train any sort of foundational model, and materials project itself has a fairly wide variety of structures and compositions present in it. So it samples more or less the entire periodic table. I mean it does not sample the rare earths quite well, but or noble gases quite well, but it samples more or less the entire periodic table for several different applications, right. So MACE MP0 is a model that was trained on materials project trajectory data set. So this has about 1.5 million structures, and it looks like the model provides fairly stable performance on 30 different properties. So some of the properties are listed here. It's able to give fairly stable dynamics in the solid state, in the liquid state, and also in gaseous states. But the model does have limitations. It works only well on cutting edge GPUs. It also has limitations on its system size, right. So MACE MP0 can only model about 2000 to 3000 atoms or so. But there are nice things about MACE. So this is an example of pore bay diagram prediction. So pore bay diagrams are used for assessing the stability of a solid in a given aqueous medium, right, as a function of pH and as a function of applied potential. So this is quite useful to consider electrochemical activity, corrosion behavior, and so on. So this is a pore bay diagram of copper based systems that was generated by materials project. So this is based on DFT data and with some experimental data, and we see that MACE is able to reproduce this pore bay diagram fairly well, and pore bay diagrams are difficult quantities to estimate accurately. So we see that MACE is able to do a good job. But having said that, MACE is not the most cutting edge model out there. So if you look at this leaderboard here, so this leaderboard is from MathBench Discovery. This leaderboard may also have been updated by the time you watch this lecture. You see that MACE is not even the top ranked model. There are models that are already better than MACE in all the different performance metrics on this materials project trajectory dataset, right. So we see that there are other models that have even surpassed MACE by tweaking the architecture slightly, by optimizing hyperparameters better, and by also exposing the construction of these models to more and more diverse kinds of datasets. So this is the construction of foundation models is a space that is rapidly evolving, and we are getting more and more accurate models as we speak. Okay. So MACE has also been used in detailed studies in the recent past. So this is an example of modeling of zeolite frameworks using MACE. This is an example of a screening study for battery cathode identification, and this is an example of analyzing how polarization, electric polarization varied in calcium titanate, a very important perovskite oxide with applied electric field, right. So here also you used MACE MP0. The authors used MACE MP0 with some custom models. Okay. So now that we have understood MACE, we will also use MACE in our hands-on session. So we will build MACE for a test system. So these are examples of graphs that you should be getting. So on the left side you should be getting this type of a graph during the training of your model. These basically indicate how your training and validation losses vary. And once you build a MACE model from scratch, you will also be running a simple molecular dynamics simulation for the system of interest. So these are basically the variation of energies as a function of time. So you see that as time propagates, your energy keeps varying, and this is your target temperature. Your system also starts equilibrating towards your target, right. So you will see that MACE is able to give you a fairly stable molecular dynamics for the system of interest. So these are some of the exercises you will be doing in your hands-on session with MACE. With that, let us now summarize our discussion on interdynamic potentials and specifically machine learned interdynamic potentials. So we see that interdynamic potentials are important for simulating dynamics in several systems. And specifically if you add in machine learning to interdynamic potentials, they can provide better accuracies than classical force fields at similar computational costs. We did touch upon classical machine learning interdynamic potentials, which are all atom centered, and here the accuracies are largely dependent on how you do feature engineering and including non-linearity and so on. In this lecture we saw the importance of high body orders, and in combination with the previous lecture we saw the importance of message passing and equivariance as well, and inclusion of all these three is fairly important for accuracy improvement. So higher body order gives you higher accuracy, more equivariance generally gives you higher accuracy, if you have message passing and more levels of message passing generally gives you higher accuracy. So these three handles give us systematic ways to construct better and better or more and more accurate models. And we saw that Maze provides a fairly general mathematical framework to create graph based neural networks and also create foundational models. We saw one specific example of Maze MP0 being a foundational model, or sometimes also referred to as an universal potential. And in the previous lecture we looked at NeckWeb as an example of a graph based neural network which included equivariance, right, and also included message passing and was able to simulate fairly large system sizes. So ACE provides mathematical framework for classical machine learning interatomic potentials. Maze provides a framework for graph based machine learning interatomic potentials, and Maze has also been demonstrated to be useful for creating foundational models, right. So with that we come to the end of our discussion on machine learning interatomic potentials. These are again fairly useful tools and these tools are also rapidly evolving. So as you keep learning in this area, you will see more and more accurate models that are available to you that enable you to do fairly good molecular dynamics simulations and also structure predictions and so on. So with that we will stop this lecture. In the next lecture we will discuss aspects of transfer learning as an example of one of the advanced topics as well. So I thank all of you for joining today's lecture. I will see you all in the next one.